All right, let's talk about the invisible science that keeps our world standing. It's a design philosophy called the limit state method. And honestly, it's the reason the buildings we live and work in don't just fall down.
I mean, have you ever really stopped to wonder, how do engineers guarantee that a massive skyscraper or a sprawling stadium or that bridge you drive over every day is actually safe? It's not guesswork, that's for sure. It's this incredibly sophisticated system of calculations and safety checks, and that's exactly what we're going to break down.
So here's our game plan for this explainer. We'll start with the absolute basics, how buildings even stay up. Then we'll take a quick look back at some of the early ways we tried to ensure safety. After that, we dive into the main event, the limit state revolution. We'll break down how it pits strength against loads, how it builds in a safety buffer, and finally, we'll see how this whole philosophy is put into practice with something called the Eurocode standard.
Okay, first things first. Before we can even get into all the fancy methods, we need to understand the fundamental mission. What are the absolute non-negotiables for any structural design?
So it really boils down to these 5 key goals. And number 1, obviously, it's got to have a solid margin of safety against collapse. That's a given. But it also has to be serviceable, and that just means it has to work, right? You don't want floors that sag or shake every time you walk on them. It also needs to be robust, which is a fancy way of saying a small, localized problem shouldn't trigger a massive, catastrophic failure. And of course, let's be real, it has to be economical. You got to be able to build it and maintain it without breaking the bank. So, any design philosophy worth its salt has to nail every single one of these points.
All right, so how did we get here? Our whole understanding of structural safety didn't just appear overnight. It's been a long journey, with some pretty dramatic shifts in thinking along the way. I mean, for centuries, building was basically a mix of trial, error, and, well, rules of thumb. Hey, this worked last time, let's do it again. But then, in the late 19th century, things started to get more scientific. We got the permissible stress method, which was all about the strength of the materials themselves, a big step up. Then, mid-20th century, the focus shifted a bit with the load factor method. Now, it was more about the loads pushing and pulling on the structure. Each of these was an improvement for sure, but they both had their own limitations. And that's what paved the way for our modern, much more nuanced approach, the limit state method. So if you look at these two older ideas side by side, you see two different philosophies, right? The first one, permissible stress, is basically saying, let's make sure the stress inside this steel beam is way, way below its breaking point. The second one, load factor, says, let's just assume the forces acting on the building are going to be way bigger than we expect and design for that. But here's the catch. They both suffer from the same fundamental flaw. They use a single, kind of blunt factor of safety. They don't really distinguish between how certain we are about a material's strength versus how uncertain we are about, say, a freak snowstorm. And that's the exact problem the next big idea was designed to solve.
And that brings us to the modern revolution in structural engineering. Look, the limit state method isn't just some minor update. It's a completely different way of thinking about safety. It's the philosophy that makes today's super tall skyscrapers and mind-bendingly complex structures possible.
Okay, so the core idea here is the limit state itself. The easiest way to think about it is like a predefined point of failure. It's a line in the sand that engineers draw, and if the structure crosses it, it has officially stopped doing its job. Now that could mean the worst case scenario, collapse, but it could also mean something much more subtle, like sagging too much, or even just vibrating in a way that makes people uncomfortable.
And these failure points, these limit states, are broken down into 2 main categories. First up, you've got the big one, the ultimate limit state, or ULS. This is all about safety, about preventing a collapse, about protecting lives. It's the absolute bottom line. But, and this is crucial, just as important is the Serviceability Limit State, or SLS. This is about making sure the building is actually usable and comfortable. Think about it. A floor that sags so much that you can't open the doors anymore, well, it hasn't collapsed, but has it failed? Absolutely. It's failed its Serviceability Limit State. So, how does this method actually work in practice? Well, it all starts by acknowledging a fundamental truth. The real world is messy and uncertain.
Just think about it for a second. The batch of concrete that gets delivered to a construction site today is going to be slightly different from the batch that arrives tomorrow. It's just a fact. And there's no way we can predict the exact weight of snow that's going to fall on a roof next winter or the precise number of people that'll be in a concert hall on a given night. This variability, this uncertainty, that is the central challenge of structural design. And the solution is pretty clever. It's statistical. See, instead of designing for the average strength of a material, which
If you think about it, means 50% of your material is actually weaker than what you designed for. Engineers use something called a characteristic strength. It's a deliberately pessimistic value. They choose a strength that's lower than the average just to be safe.
So how much lower? How cautious are we talking? Well, the characteristic value is a strength that 95% of material samples are statistically expected to beat. Let that sink in. This means engineers are starting their calculations with a strength value they can be incredibly confident the material will actually have in the real world. They're building a huge margin of safety in from the very beginning.
But that's only half the story. On top of using these super cautious characteristic values, the method adds another, really intelligent layer of safety.
Okay, this looks a bit like math, but the core principle is actually super simple. The goal is easy. The building's resistance has to be greater than the load trying to break it. Simple, right? But the genius is in how we calculate those two sides of the equation. For the resistance side, we take our already cautious material strength and we make it seem even weaker by dividing it by a safety factor. Then, for the load side, we take our best guess of the forces and we make them seem even stronger by multiplying them by another safety factor. So you see what's happening? We're designing for weaker materials and stronger loads at the same time, creating this powerful safety buffer right in the middle.
But wait, why have two separate safety factors? Why not just one big one like the old days? Well, this is arguably the smartest part of the whole system. It's because our level of uncertainty is different for different things. For instance, we have incredibly tight quality control over steel made in a factory, so its material safety factor can be pretty small. But trying to predict the absolute maximum wind speed a building will see over the next 50 years, that's way more uncertain, so its load factor needs to be much, much larger. This method lets us intelligently apply safety margins exactly where they are needed most. It's rational and it's economic.
Now, this powerful philosophy isn't just some abstract idea in a textbook. It is the engine behind the most comprehensive, most advanced design standards used in the world today.
Yeah, the limit state method isn't just a theory. It is the absolute foundation of the Eurocodes, which are widely considered the most advanced set of structural design standards on the planet. When an engineer designs a complex modern structure today, this is the philosophy they're putting into practice. And the scope of this thing is just massive. There's a Eurocode for the basic principles of design, another one just for loads, wind, snow, people, and then you have specific codes for concrete, for steel, for timber, masonry, and even for geotechnical design. That's the ground the building stands on. It's a totally unified system, and it's all built on that same core limit state philosophy. That ensures a consistent, high level of safety across every single part of the construction process. And look, this isn't just me saying it. This is a recognized fact in the engineering world. The massive collaborative effort to produce the Eurocodes, based on decades of research and real-world data, has created a system that is respected globally for its advanced and rational approach to keeping us all safe. So we've gone from an ancient art of trial and error all the way to a sophisticated, statistics-based science. The way we guarantee our safety has been completely transformed. It's this hidden system, this invisible layer of cautious estimates and targeted safety factors, all working together to make sure our world stands strong. So the next time you walk into a building or drive across a bridge, maybe you'll think about that invisible statistical shield that's keeping you secure. And now you know how it works.